So there's a couple questions on the homework. These were the last couple, but it looks like for the most part we're doing okay on the homework. I want to make sure that we fully understand what's going on here, and I'll give you an alternative way of doing this problem. I don't like the alternative way, but it's an option. You guys remember, so when we've got a polynomial here, okay, minus then another polynomial, right? And this set of terms over here, this polynomial is in parentheses, so that means remove the whole thing, right? Okay. We can't. And the number one error is that people just get rid of like that parenthesis. So when I get rid of that parenthesis, the negative gets stuck to the 8x squared, right? But when I get rid of that parenthesis, I get rid of this one as well, and I actually end up removing a 2x, which if I would have distributed correctly, I should have added a 2x. And I end up adding 7, but if I would have distributed correctly, I should have subtracted 7. So you can't just get rid of those parentheses and do what's there. Does that make sense? You, first thing, always have to distribute. So I want you to distribute that negative to there, and to there, and we're going to rewrite. Okay, so it's going to be rewritten as 7x to the fourth plus 4x cubed minus 1, right? The first part doesn't change at all. Didn't distribute to anything there. Now if I distribute that, 8x squared becomes negative 8x squared, right? The negative 2x, what's a negative distributed to a negative 2x going to become? Positive 2x. And then a negative distributed to a positive 7 is going to become negative 7, right? So now we go through and we're just going to look to see, okay, can I combine any like terms? Are there any other things? What identifies whether I want to have another like term that will match with that 7x to the fourth? There are none up there, but how are you telling me that there's nothing? Why do you know that?
Because nothing else has x to the fourth.
Okay, so I'm looking for something else that is x to the fourth, and I don't have any of those. So 7x to the fourth is going to be part of my answer. Okay, I'm done with that one. Then I go to this one. Are there any other x to the thirds?
Yes. No.
Nope, so I'm just going to write plus 4x cubed. I then get to this one.
-7.
Okay, and that can match up with the negative 7. And you got to make sure that you take the signs that are in front, right? You got a lot of people say negative 1 and then 7. So that gives them like 6. Or they take 1 and negative 7. They get negative 6. If I go negative 1 minus 7, what's that going to actually give me? Negative 8. Okay. Any other x squareds?
No.
Nope. So negative x squared or 8x squared. Any other x's? Nope. So 2x. So now I want to rewrite this so that's in descending order. So that means largest exponent first. What's going to be next? 4x to the third. And then what next? Okay, then what? Plus the 2x, and then minus 8. Okay, so that is what we're looking for when we're going to subtract those two things. Okay, now I want to draw a comparison to what you may saw on a question like number 10 or something. In your homework, let's see here.
When are you assigning A2 tomorrow?
Yeah. We're going to have a lot of birds. There's like 3 nests out in the tree out there.
There's a 3 out there? Yeah, I took out the birds out. Smart. Thank you.
All right, so did you guys have any issues or concerns with this problem here? All right, so let's look at this. So they're going to present it this way sometimes. This is equivalent to taking, if we were to write it in the same format the last question was in, it would be 3x squared minus 3x plus 3 minus then the 6x squared plus 5x minus 5. Does that make sense? Okay. I don't like stacking them this way. Okay. Because I'm going to mess signs up, and I think just per previous students, a lot of times we mess signs up. But if I stack these like this, we recognize the reason they like to stack them is because those are all x squareds, right? These are all x to the first. These are all constants. So it aligns or matches your like terms maybe a little bit better. Does that make sense? But the reason I don't like it is because I got to go 3, now minus 6. That's not bad. What's 3 minus 6? Negative 3. So we get negative 3x squared. Now here's where I don't particularly like this. What's negative 3, and then this minus, and then a positive 5. What's negative 3 minus 5? That's where I don't like it. Negative 3 minus, this turns into, because a minus a positive is just a minus, right? Does that make sense? So it's going to be negative 8. And now if I've got 3, and this is another reason I don't like this, 3, then this yellow minus, and then a negative 5. What's 3 minus a negative 5? That's positive 8. Right? So so that gives me the answer. This is the reason I like doing this better. If I distribute that, I have 3x squared minus 3x plus 3 minus 6x squared minus 5x plus 5. And now 3x squared minus 6x squared. Is that going to be negative 3x squared? Make sense? If I go negative 3x minus 5x, does that give me negative 8x? Yeah. And then positive 3, positive 5, and positive 8. That kind of makes sense why I think that's a better route. Now you can do this, and I told the last class they can do this. So subtraction is adding what? Adding the opposite, adding the inverse, okay? How do we want to phrase it? Adding the opposite, okay? So let's do this. If I want to, so right now I've got subtraction. Let's actually add the opposite of this. So if I go 3x squared minus 3x plus 3, I want to add, but instead of adding this, I got to do the opposite of this. So I get negative 6x squared would be the opposite of 6x squared. Negative 5x would be the opposite of positive 5x, and positive 5 would be the opposite of negative 5, right? Now if you add straight down, you get negative 3x squared, you get negative 8x, and you get positive 8. So you can do it that way if you want to. I prefer the initial way that I showed you yesterday, but it's up to you.
Add the opposite and the one that adds the negative sign.
Yes. So that's all, because that's all subtraction is, right? Adding the opposite. So when you see something like that, you can attack it that way. What'd you say?
Yeah, a couple of times.
Yes, because this matches up the systems of equations, right? Remember when we had, like if I had like 2x plus 3y equals 7, and this was 2x plus 4y equals 8, we would always want to add down, so we basically wanted to subtract them, but I added down by multiplying each one of these by a negative, and that's really what happened. So yes, we did do that a couple chapters ago. That's a good connection. The one thing that I want to make sure you understand that if you do that, so let's come up this question up here that we just did. If I were to line these up, and this is another reason why I don't like that strategy. If I start lining these up, so let's go 7x to the 4th plus 4x cubed minus 1, okay, and I subtract, are there any 8x squared, are there any x squareds that I would line that 8x squared up with? No. Okay? So this is really what has to happen if you are going to stack these. You have to put in a 0x squared. You have to put in a 0x. We call them placeholders, but we need those because now I can put my 8x squared right there. I can put my minus 2x there, and I can put my positive 7. And now like terms are lined up, right? But that is problematic because a lot of people forget that they need those placeholders. They don't line things up correctly, and they start adding the 7 and the 8, the 4 and the 2, and the 1 and the 7, and it messes things up. Okay? We cool with that? All right. So this one. What's perimeter mean? Okay, so it's the length or the distance all the way around, right? Okay, so add up all the side lengths. Okay, so last class, this made a lot of sense to them by doing something like this. Give me a value for x. 4. So what's 12 times 4? 48. What's 48 minus 2? 46. So if x is 4, the perimeter here would be 46, right? If x was 4, what's 4 times 16? 4 times 4. 16 minus 4 is 12. Okay. And now if x is 4 again, 2 times 4 is 8 plus 3 is 11, right? Okay. Now if I ask you to find this side over here, let's just call this T for third side. If I want to find that third side, knowing that they total 46, and you have 11 and you have 12, what can you do with those three values of 46, 11, and 12 to get T? You're going to add what?
Add 11 and 12 together.
Okay, so what you're going to, so you can do that in maybe 2 steps. And I guess it doesn't really matter. You said add these together. Okay, so you would take 11 plus 12, and that gives you 23, right?
Can I pull up mine to show you what I did?
Yeah. So you're gonna get 46. Add those together, you get 23. If I subtract those, you get 23, right? Does that make sense? Now remember, how did you get this 23? You took the 12 plus 11. Well, let's go back to that 12 was 4x minus 4, and the 11 was generated because of that 2x plus 3, right? Does that make sense, everybody? So that's the thing that created the 23. What was the thing that created the 46? 12x minus 2, right? Then we take 12x minus 2 minus the 4x minus 4 plus 2x plus 3, right? So can I combine some, it depends on how you want to do it. I think most people would probably combine the like terms inside these parentheses first. What's 4x plus 2x? 6x. And what's negative 4 plus 3? Negative 1, right? So now can I go 12x minus 2? What do I do with that negative? Distribute. So we get negative 6x plus 1. How many x's then will you have? 6 of them, right? So you get 6 x's, and then what's negative 2 plus 1? Negative 1. So that would be the way of doing it with generic values. But let's think about it. Let's see if this makes sense. If x was 4, what would 6x minus 1 look like? Be 24 minus 1, right? Which is 23, correct? Yeah. Is that the T value that we found when we tried it with 4? Does that kind of make sense? So here they're trying to get you to take a total that is represented by an algebraic phrase, 12x minus 2, and start subtracting away parts of it until you can find that last thing. And one of the big things that we do in geometry is if you know like the total of something. Let's say we talk about, does anybody know how many degrees 3 angles of a triangle add to? 180. Okay? So if I give you one of them to be 50 and one of them to be 40, what's the other one? 90. You took 180 minus 40 minus 50, right? So same kind of concept here. I gave you knew a total 180. You knew 3 things made it. If I give you 2 of those things, you can find the third one, right? So here, we know the perimeter is the sum of those 3 sides. We know the total. We know the perimeter. We know 2 of the individual sides. If we do some subtraction, we can find that third side.
Yeah.
Okay. Say again?
Yeah. I can already get you 180, and then you have to find 180. Saying there's different.
Well, I don't understand what you're saying.
But you didn't give 180, right?
Okay, I see what you're saying. Yes. Yes.
So, like, for that, basically, just like what I do, I guess, like, every step you use.
Okay.
And, like, I only subtract them.
You subtracted.
Okay, so look. Come here. Look at this. I added that.
Yeah.
and I did that, and I did that.
Say again. Start again. Start from the beginning.
I just basically added these two
Yeah.
and got that. Like I added those, and then whatever I got, I subtracted from that and got that. You know what I'm saying? Because like 4 plus 3 is 7. And
and then subtract that from 3. And that's exactly that's what we did here. So when you add yours two together, when you add these two together, that's what I'm doing right here, right?
You just plug in a number for that.
Yeah, I plugged in a number just to see, just to make the connection of what I'm supposed to do with these variable parts.
Okay.
Yes. Yes. Do you guys have any other questions on that assignment? Anything else that's causing issues, concerns? Why don't we,
Wait.
Sure? All right. Let's go to this. You guys know what GCF stands for? Greatest common factor. So what is the greatest common factor then?
The greatest common factor?
Well, what is that?
It's the greatest number
that can multiply with something. It's the greatest common number. They're all like, no. I'm going somewhere. List the numbers and they all have like something in common, like one number in common.
Okay, so what is the thing though that we what is the mathematical idea that is wrapped up in the idea that they have it in common? What does that mean? What does that in common mean? How do I know that they're in common?
Because you circle.
You're close.
Yeah.
When I look at two numbers, how do I know what's factor stand? What is a factor?
A number, right? That's a good question.
It is a number, but what do you do with that number?
You multiply it with another number to get that number.
Okay, so factors are things that you multiply. So let's say 2 markers, 3 markers, right? 2 times 3 gives me 6. So 2 and 3 were the what? No, they were the what to get 6. They were the factors. Okay. The word factor. What does this mean? Somebody asked me last period to do that. What does that mean?
It means you're trying. It means you're trying.
What?
It's what shy people do.
You're not
Trying to do that.
You get why it's like that.
Shaking your head.
No, I don't get that.
She's shy and you're making the face.
Like that's the shy face?
You're telling me. Not doing this means you're shy.
It's a TikTok.
Of course it is.
All right. So factors are things you multiply together to get a what? Nope. When I multiply two things together that are factors, I get a no. That's division, and it's related. No. Want the first letter? P. P. All right. Product. Okay.
I knew that.
So we're gonna multiply two numbers together to get a product. So if I give you 2 times 3, you know those are factors that give the product of 6. We know how to do that multiplication. How can I undo multiplication? What if I say I give you 6 and I ask you to figure out what are the factors for 6? How do I work to find out the factors? So I divide. So I undo division or undo multiplication to division, right? So what's going to happen here, if I give you a number like 6 and I ask you what are the factors, you're going to divide it by 2 maybe. And what do you get when you divide 6 by 2? 3. So 3 is called the quotient in that division, right? But the quotient and the divisor are products or factors to make the dividend. Let's write this down real quick. Let's write an example here. So I don't think, and I wish that this was explained to you a little bit more detail when you're in like the 4th or 5th grade. But I think it's just assumed that at that stage and maybe later on that you can pick this up. Give me a number. Give me a Give me a composite number. Do you know what that means?
12.
Okay, so 12. 12 is a good one. Okay. Okay. 12 divided by 2 would give me what? 6. Okay. So that is 6 is called the quotient. Remember that? Okay. 12 is referred to as the dividend. Okay. 2 is called the divisor. Okay. Now what happens is that we can find out that the quotient multiplied by the divisor is equal to what? If I take that quotient of 6 and that divisor, multiply them together, what do I get? I get the dividend. Okay? So these are factors to that product. Does that make sense? So if 12 is my product, through division, I can determine my factors, right? So whenever we work through this course or any other math course and they say, factor this, or solve this equation through factoring, all they're asking to do is figure out what things multiply together to give me that. Or it's a fancy word for division. Does that make sense? Distribute, fancy word for what process? When we say distribute, what operation are we doing when we distribute? Multiplying. Okay? The undoing of that is called factoring. So the undoing of multiplication is division. So factoring and division go together. They're the same thing. Just fancy words for the same thing. Distribute and multiplication, fancy words for the same thing, right? Multiplication undoes division, division undoes multiplication. Factoring undoes distributing, distributing undoes factoring. Okay? Let's talk about some numbers that do not factor neatly. Like 2 is one of them. Yes. By definition, it says a prime number is a number that is greater than 1 and is only divisible by 1 in itself. So 13 is a number like that, 17 is a number like that, 5 is a number like that. Careful. What's 25 divisible by? 5 and 25. So that's not just 1 in itself. 26 divides by 2, doesn't it? 21, 7 and 3. 29 is 1. Okay. 31 is 1. 3 is 1. Okay. What's the smallest prime number we come across? 2. What's the only even prime number we come across? 2. Okay. So these other numbers like 4. So what I'm saying here is like if I were to do, you guys have done factor trees, right? Okay. So let's do a factor tree. No. Ruin that person's day.
Like Mr. Say here.
Hello? Yes. Okay, I should be on my way.
Is this for me?
Thanks. Bye. All right, so, no. I don't care what she thinks. All right, so if I've got 12, give me 2 numbers that multiply together, give me 12. 6 and 2, 4 and 3 would be fine as well. It doesn't matter how you do it, because I'm going to stop when I get prime numbers. Is 2 prime? Yes. So now I'll keep going with 6. 2 numbers multiply, give me 6? Okay. So I'm stop at both those. Those are prime, right? So if you went 12 is equal to 4 times 3, do I still get 4 to go down to 2 and 2? And that's the reason. Does that make sense? So no matter how you do it, eventually if you stop at prime numbers, you're going to find out that 12 is 2 times 2 times 3. Those are what we call the prime factors of 12. Okay? Because we're using numbers to multiply to get 12 that are not 12 and a 1, that is not a prime number. Does that make sense? 12 is not a prime number. And if it's not prime, does anybody know what it's called? Composite. Okay? When you are in English class, what do they say when you're writing a paper? What are you what's that process called? Starts with a C. Close. You are composing something, right? If I'm in music, okay, I'm composing something, correct? What does that mean? When you're in writing, you compose something. What are you doing? What are you writing? What do you mean?
Compository text.
Yeah.
What did you just say?
That's like composing, right? Compository.
So if I compose, when we say compose means to put things together. Okay? Yes. So something that is decomposing is falling apart, right? Okay? So composite numbers are numbers that we've used multiple numbers to put together to get something else. Does that make sense? Okay. So 12 is composite. 45, is it prime?
No.
No, what multiplies the other give me?
5.
Okay, so I can rewrite this as 3 times 3 times 5, right? Okay, so is that prime or composite? That's composite. Okay, let's do 228. What number divides 228?
222, 8.
Okay, 2 and Jaden, what'd you say? 114. What divides 114? 2 and
8. 6.
57. So how am I getting that second one? I'm taking 114 divided by 2, right? What divides 57?
Nothing.
Nope.
13.
3.
Oh!
Okay. 3 and 19. What divides 19?
Nothing.
Nothing.
8 and 2.
Other than
9 and 2. I mean, what's 19?
19 and 1. So 19 is what kind of number? Prime. So I stop there. So when I multiply this, I get 2 times 2 times 3 times 19, right? Okay. Now my question is, let's look at these things. Let's look at these three numbers. What do they all share? They all have a 3 in them, right? Okay. So 3 is the largest number that divides all three of those. So 3 is the the greatest common factor, the GCF. Okay. Now if I look at let's look at these two. Okay. What do they both have in common?
3.
Just a 3. Okay. So the GCF of 12 and 45 is just 3. Okay. What about?
All of them have 3 in them.
Well, yeah, but what if I look at just these two? What do they both have in common? 2, another 2, and another 3, right? Okay, so what's a 2 times a 2 times a 3? 12. So 12 is the largest number that will divide 12, and it's the largest number that will divide 228. So that's the GCF of those.
Oh, that's cool.
That kind of make sense? 12. Okay. Now, when we say divide or is divisible by, okay, what we're meaning there is that we get a whole number quotient. So when I say, I could take 10 and divide it by 2 because I get 5 back, right? But I could take 10 and divide it by 3, can't I? But what do I get back? 3.3333333 forever, right? So that we would not say that 10 is divisible by 3, even though we can do that math and get a result. When we say the word divisible, we're meaning that our quotient is terminating. It's a whole number. Okay? So that's what we're looking for when we talk about common factors or GCF. What is the GCF between 8 and 12? 4, right? So that's the hope. Is that, we can write these all down, kind of doing the factor tree and then highlighting things they have in common. But my hope is that eventually we can just kind of see them or recognize, okay, maybe do a quick check. Does 8 divide 12? No. Does, what's the other factors of 8? 4. 4 divide 12? Yep. So that's kind of the approach that we're looking for. So 4 divides 8 and 12, that's the largest factor. What about 3 and 15? 5 divides 3?
3.
Remember, we're trying to find the biggest number that divides both those, right?
3.
So 3 divides both those. What about 20 and 200? 20 divides both those. Okay? Not always will, we saw it here with the 8 and the 12, not always will one of the numbers be the GCF, right? In the last two examples, the 3 was the GCF and the 20 was the GCF. That won't always be the case. And sometimes there won't be a GCF. So if I say 2 and 17, are there any common factors that divide 2 and 17? No. Okay. So they don't have a GCS. There is actually, and it's you guys, I don't know if we've talked about this in the past. It's called, you guys know what encryption is?
No.
So like when I send, like, let's say that I just have like Venmo or PayPal or Apple Pay or something like that. Let's say I send Ollie some Apple Pay. So I give him access essentially to a little portion of my bank account, right? What guarantees that he can't use that to get actually into my bank account and steal all my money? It's called encryption, okay? What allows me to send an email and be confident, for the most part, that email is only going to be given or sent to the person I sent it to. It's called encryption. What encryption is it basically takes our message and it puts it down into a bunch of numbers, okay? Essentially zeros and ones. But it takes our message and makes it into a number. We then multiply that number by a very, 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 very large prime number. And when I say very, very, very large prime number, I'm talking millions of decimal places, okay? Or millions of place values. We multiply those together and we get a product, right? That big number that is the product is what gets sent through the data waves, okay? So it gets sent through the telecommunication lines and all that kind of stuff. Does that make sense? And that then gets to Ollie's phone, his computer, whatever. And that device then has the programming, has the software that basically undoes that long number. Well, if we sent that long product through, how is his phone going to undo that long number? Is that it's going to divide it by what we initially multiplied by, right? Does that make sense? Okay. So I'll give you kind of an example here. Let's say, and we're going to use kind of small numbers, but imagine these are very large. So let's say that my message to Ollie is put down into like this number. Let's go. Let's just say 25. Okay. So 25 is my message. Okay. When I send it, okay, the computer or the software or whatever, the software multiplies that 25 by a prime number. Let's just give me a good prime number here.
4.
Let's go 7.
7?
Okay. And that gives me a new number, right? What's 25 times 7?
135. Wait, am I right?
If you had 7 quarters, how much money you have? 175.
Oh, close.
Okay. So 175 is my encrypted message now. Does that make sense? And that is the number that is sent through your telecommunication lines. Okay. Your broadband, that kind of stuff. Does that make sense? Okay. That is then received in, let's say, Ollie's phone. Okay. So it's receiving his phone. He's got software in his phone. His software sees that as 175. The only way that his software can demonstrate or produce this message of 25 is to know that 25 was multiplied by that prime number. Does that make sense? So his software is going to be coded with that prime number. It's going to take that 175, divide it by 7, gives him 25, gives me his message, my message, and he can read it. Does that make sense? Now the purpose of this is because when this 175 is out here in these data lines, there are hackers that are trying to pull that 175 out, right? Well, they can only tell me what that message is if they know that number right there. Does that make sense? Okay. So if I'm using a number small like 7, my hacker, all I have to do is say, okay, 175 divided by 1. Does it give me a message? Nope. 175 divided by 2. Does it give me a useful message? Nope. 175 divided by 3. Does it give me a useful message? No. And they go up to 7 and they find out, 175 divided by 25. Oh, it opens up this essentially locked door to me and it gives me my message. Does that make sense? Okay. So that would be pretty, because it's a small number, computer programs would be able to check 175 divided by these small numbers very easily. So what do? We make that number a prime number that has millions of decimal place values before we see a decimal, okay? Or so millions of placeholders. And that is then sent, that huge number sent. So now when a hacker steals that number in the data line, their computer programs cannot break it. Does that make sense? Okay. So prime numbers are what I think you guys should probably be very interested in, because they keep your messages, your bank accounts, your money safe for the most part.
So then, like, how that's
Now, so sometimes you get hacked, right? sometimes your stuff gets hacked. And what that basically means is that the prime numbers that are being used for your encryption were not big enough. Okay? And basically the computer program that the hacker has was able to use and figure out those large numbers. So there's an entire sector of the private world, private business, that is trying to find what is the largest prime number. And the idea is that, there's a lot of math, there's entire branches of math that are devoted just to seeing what are the patterns of prime numbers. Because early on, 2, 3, 5, 7, 13, 11, okay? Within the first 10 numbers, there's 6 of them that are prime, right? Or 11 numbers, 6 of them are prime, okay? Eventually, to find 2 prime numbers back to back, you have to go millions of values between the two, okay? So there's mathematics to say, okay, well, if there's so many early on, and they start to gap themselves, okay? Let's see if we can find a list of prime numbers real quick. You can see early on, the prime numbers, they're all pretty close together, right? Okay? But eventually, they start to get a little bit more spread out. We go from, now there's 4 between these two. There's 7 between 47 and 53, or 6, I guess. Okay? But there's a pattern here. So every once in a while, you'll see, like these two are 2 apart, right? Let's keep going. These two are 2 apart. I see others that are 2 apart here.
101 and 103.
101, 103. 191, 193, right?
113, 127.
3 and 5 is 1. 197, 199. Okay. So we start to see that they come up in pairs like that, right? And what happened, I don't know how long this list will go. Maybe I'll find another Wikipedia list here. Okay, so these are larger, right? Okay. But eventually, there will be numbers like these two that are 2 apart. Okay, so those are prime number pairs that basically mathematicians are interested to see. Does that pattern exist when we have 100 million place values as our prime number? Okay, huh? Eventually, the ones I highlighted a minute ago, they weren't, but eventually they'll. Like these two, they're not 2 apart, but as we get larger and larger, so these are 6 apart, 6, 6. I don't know. We could go through here and eventually find some that are larger and only 2 apart. So here's 2 apart right here, right?
What is that?
So that's a prime number. That's a prime number. But see how there's only one even number between the two? So that's a pattern that exists for prime numbers a lot. All right, so here's my question. Look at these numbers. Okay, now they're variable, right? There's some variable components. What kind of number is 5? 5 is prime, right? What does x to the third really mean?
X times X times X.
X times X times X. Okay? Now remember that X is a number, so it could be a 2, a 2, a 2. It could be a 3, a 3, a 3. It could be a 5, a 5, a 5. It could be a 7, a 7, a 7, right? Okay? What's 25? 5 times 5, right? What's x squared really mean? X times x, right? And remember, x are just numbers, correct? Okay, what's 45? 5 times 9, but what's 9? 3 times 3, right? And then the x is just times x, right? Now remember, the x's are numbers. The x's are numbers. So let's go through here and highlight what all of these share. Do they all share a 5?
Yes.
They all have 1 5 in them, right? Do they all have 1 x in them? And remember, that x could be another 5, it could be a 2, it could be a 1, it could be whatever. But they all have that. Do they all have a second x? No. So this one has a second x, so does this one, but this one doesn't, right? Okay, so I'm wanting the values that are repeated in all of them. So this one doesn't have this one doesn't have another x, this one has another x, but this one doesn't. So I'm done with the x's. I'm not going to see, because this one only has 1, so it's not going to have 2, it's not going to have 3, it's not going to have 4. Do any of them have another 5?
No.
Right, but so this one doesn't have another 5, but that one does, right? And that one doesn't. So do they all have 3s in them? No. Okay, so what I'm trying to do is find out what is the maximum number of things that they share. and they all share 1 5, and they all share 1 x, right? Multiply those together, what do you get? So multiply 5 and x together, I get 5x. Does anybody want to know what, or guess what 5x is called for those 3 monomials? It's the greatest common factor. It's the GCF. Okay? So 5x is the GCF here. So tomorrow, my main focus for you guys is, because we understand what GCF is with numbers, with integers, let's work with GCFs with variable monomials. Okay? So we're going to basically break everything down that way and see what they all have in common. Okay? The hope is eventually we can look at that and just say 5x. We know right off the bat. Okay? But initially, we'll break it down this way and just kind of highlight the things that they share. Is that cool?
Yeah.
8.2, I don't know. It might show up, might not. I don't know if what I've done with that yet. It's not due tomorrow. Because it's not going to be due tomorrow, I'm actually extending last night's homework 1 more day for you. Okay? So last night's homework isn't going to be due until tomorrow night.
Were you there? The meme of writing table.
Come here.
Like after Juliet potion.
Oh my God.
You weren't there? You put on.
Are you ready for our quizzes today? What? They got my potion.
No, we don't.
These are art. We did not pay for
Just what? You do board work. You do board work today.
Oh my God.
What is this?
Yes.
Is this geometry?
Yep.
Why does it look really easy? Is it really hard? Isn't it where you like take those and you have to find out what C is that you want to?
They're going to try to find, like, the length of AC and the length of CB.
Oh, we did that
segment.
I hate it. I hate anything triangles and that.
SOHCAHTOA? SOHCAHTOA? Sine, cosine, tangent?
Is it easy?
I think this is one of the harder things that they've done so far this year.
I don't know if I heard there was like something last week that was really hard.
I don't know what would have been hard last week.
We wrote down on the board. Imagine being nervous.
I don't know. Olivia drew the other stuff. Is that the same handwriting?
No.
No, it's not working.
Madison Mole asked me if I was nervous. I don't know if she then wrote that. Oh.
You nervous, Mr. Ray?
Like, what would I be nervous? What does that mean? That's shy. What?
Shy person, have you ever seen that? Yeah, you gotta point them. It's not just like make some soup like that.
Ow, Mr. My head got stuck over there.
Have you ever had a green Gatorade?
Hunter, you took it? Give me my Gatorade.
How's it going?
Pretty good. How about you?
Oh, sorry. I haven't looked at what they're doing today. Earlier they were up like 200, but Smile. Smile.
She's sick.
Smile. Yeah?
Like ammunition.
Good morning, Mr. Beck.
How's it going?
Afternoon.
Smile, fellas. Could be going into battle somewhere. RJ, I read an article about 13, 14-year-old boys back in the Civil War going into war. So you could be that. My grandfather, when he was 17 years old, how old are you, 16? And my grandfather, 17 years old, entered World War II on his own. You could be doing that. So, I mean, yeah, doing Sokotowa or getting shot at by Germans.
Yeah.
Hey, Jimmy, you gonna be late? Ball.
A what?
A ball.
I know, but like, how'd you get it like
I just squeezed it.
Yeah, he has.
Big Mac's on you.
Oh, I made it there.
Big Mac's on you.
Where's he at?
I heard we had a quiz on Friday.
Yes. Adios, Sergio.
Yeah, I have it next week.
You want to do it either tomorrow, today or tomorrow? It doesn't matter. Okay, that works. Just come on up, come back up.
Will, let me have it. Yeah. Dude, sick.
You make that step from the right. Just get a hammer, Mr. Baby. Hit it as hard as you can. What is a big bullet?
Yeah, Sam's like
Hey, let me see that.
Oh, yeah. Wait,
You
dude,
can
hop
sit right
in.
here. Sit right here. I'll take care of it.
I got it. Will, quick hop table. Did you make this thing?
Let's see who drops it first. Drop it in. I'll go over there.
Just my lunch.
You sit in Big Mac. I'll put it right here. And we'll throw it back.
Like a bell ring. Or you're holding something.
Not very long.
Not very long. I'm proud of you.
Well, thanks.
Are you making fun of me? Not anymore.
No.
That's my little You are watching more.
I took you around. Yeah, I took myself.
All right, folks, let's get our notes out. All I want to do today is go over a couple example problems. Maybe introduce the ambiguous case to you. Let's not throw things, especially babies. You're only supposed to do that when they're alive.
I want to see your face. Like when you were holding your baby, like when they were first born, I just want to see your face. Because like you look, I don't know.
That, it was like that, right there.
Not,
I have that face of like, oh god. I was like,
but you look like
So I actually just look, yelled at him.
Put it in the chair in front of you.
Toby just froze him. Toby would be like, it's still crying, and then take it.
That's what you're supposed to do to him.
Stop crying, baby.
Yes, that fixes it.
Yeah, I mean,
Stop.
Forever. Forever. Like in the squeeze, the
Yes,
body
sir,
part
okay.
the body will pop off, the head will pop off. Like with a baby powder bottle, you just squeeze it and the top flies off and all the powder flies out. I think I do that with the baby. Let me see it, let me try it.
I'm good.
Five.
I kind of want to do grade.
You think Mrs. Raychok would be mad?
This is his baby got plastic on.
Really?
Got what?
Somebody stole a baby at lunch.
No, Mrs. We all wanted to show Heidi like their baby. So we all went in there and Kiara was like, I don't want to take it in there. So she left it out there and Miss Miller came over and started playing with it the rest of lunch. And she just took it.
Mother of the year.
I would put it in my face.
Yeah, I'll leave it in my car.
It's in a baby bag. Windows are out.
Yeah.
Stuff it right here.
Just the head's right here.
No, wear your sweatshirt backwards. Put it in the sweatshirt.
Oh, you know what? Good point. Good point. Or you can take like one of those, you know, those like quick wall things where like you like push here and then like it'll grab there.
RJ, who are you texting? You all gotta understand that when you got a bag in front of you and you're just sitting down there doing this, staring at it, like you're not playing Xbox in there. I know you're texting somebody, Snapchatting, aren't you?
Snapchat. Are you Snapchatting, RJ? I keep this in the
Sure.
Yeah.
You can have my trash.
I'm very happy. Does it bounce? Check this out, dude.
Okay.
Oh my God. It doesn't tell. That bounced up in the air. Now it's not, my day is ruined.
Around on the other side.
I just
Make it into a square.
Good point.
All right, I need you guys to, yes, and I want you to find for me, not that one. Not that one.
I never know how to find the angle.
That's the one I want to find here.
Not that circle. Do
So you want one where we got to find angles.
Please don't make it hard.
Why?
Because you won't challenge.
You don't grow if it's not challenging.
I'm having a hard time.
If it doesn't challenge you, it doesn't change you. Good.
Now you're a better person. And you're better. Look at it. You're better.
All right, so let's say that this angle here is, what'd you say? 42 degrees. Okay. Give me a number for this side. 15. Okay, give me a number for this side.
35.
Okay, you just made this problem really difficult.
I did.
Yep.
Way to go.
Erase it. Erase it.
Solve, or at least set up to where you can solve for X degrees. I want you to find that angle up there. Just set the proportion up. That's the minimal amount of work that I want you to do. But if you can go further with it, go further with it. And I got to find something on here to show you.
Does your pen thing work on your board?
No,
Why not?
because they don't.
Why don't they? They should.
They should, but they don't.
This side can go this way.
Even though it's frozen, but yeah.
Oh, I'm sorry. My magic power.
I've been trying to.
Speaking of Elsa, singing Let It Go from the theater. No, you're not. Yeah, I am. I'm being dead serious with it.
In her office.
What? No, I'm right now in office. And Mike just come out and dress. Don't know yet.
Make sure you have a fake.
Oh, yeah.
You're gonna have the fake.
That's an appropriate one. Their theater.
What's it called today?
Wall sign.
No, wait, I'm learning.
We're not going to get that far today.
That's just not attractive.
No, is that 42?
Really on how she helps the baby on the desk.
Mike keeps saying domain error.
You're putting it in wrong.
No, I'm not.
Oh, you are. And Chicago, that's what happened for me.
Let me double check real quick.
I remember
Oh, yeah, that's what I got.
Sometimes the way that things get set up. Let me see, 42,
Because when you put this,
35.
35 times 42 divided by 15 is above 1. Because I was more than 1.
I did it wrong.
Yeah, I got domain error. Huh. And you're not so smart now, is it?
No, listen, I put the wrong number.
Let's make that. Okay, so if you've just set this up, let's change that 35 to 13 will be a better. 30. So 35. What happens is, and this was, I probably should have thought about this before. The sign function can only, when you type in the sign inverse, the ratio, the number has to be between -1. So let's just say -1 to, I don't want to use that letter. I'll just say X to 1. Okay, it has to be between those two numbers. So the quotient that was working out there was greater than, per what you were saying, greater than 1. So this hopefully will work. You should get an answer here. If these two are pretty close to being the same value, right? If those were both 15 or both 13, what would you tell me about those two angles right there? They would be identical, right? So because they're off a little bit, this one should be around 42, but you should know that it is what compared to 42? Is it the same, or is it less or greater? Should be less, because it's across from a side that is smaller than 15, okay? So that can all give you kind of perspective on what your answer should look like when you're done. Once I find this applet, I will get back with you. Open, recent, circle, sign, export to.
35. 0.444. 37. Ian, I missed you at long jump yesterday. You were there, I didn't have to miss you. Because he wasn't there? No.
Did you miss me, Keaton?
Oh. Yeah, that's it. Sometimes. You have chalk?
Not quite. DMOS, don't know what happened.
All right, so we're looking at, so I'm going to say this and that have to go together, right? Okay. So when we write this, what always goes in the parentheses of any sine, cosine, tangent? The angle always goes in there. So 42. So this is always a distance there, right? Okay. Equal to now the sine of what other angle do I have to put here now? I have to put x. Okay. And then what is going to go down here? 13. Okay. So again, we get that idea. When I can circle those things like that when they're opposite, and only one of the things that is circled is a variable, I know that the law of sines is going to work. Okay? And that's fine. So So when we have sine of A over A equals sine of B over B, we know that because of, if we go A over B equals C over D, when I cross multiply, do I get AD equals CB? When I flip-flop them and I make it B over A equals D over C, do I get AD still when I cross multiply those two, and CB when I cross multiply those two? So you're allowed to take reciprocals, right? So if you do it wrong and they give you feedback or review an example or something like that, if those are on there, they might give you A over sine of A equals B over sine of B, okay? Sometimes, even like say, let's say, and I don't know, I'll look at the reference sheet here to see if we can get a reference sheet that does this. See here.
Flip double light. Average student by day, shot it by night.
All right, so this is the end of course exam review reference sheet. So they don't give you the law of signs on here, but they do give you Stochasella, which is nice. They give you special right triangles, which is nice. But that's the formula sheet that we get. Sometimes, so if I'm working on a question and they start the question, there's a lot of questions that the end of course exam deals with, or even the ACT, sometimes we'll give you a little blurb about what you're supposed to use. They might say the law of signs formula is, and then write what's in red there. Well, that's different than what we've seen, right? It's different than what we introduced to that yesterday, but it's generated from knowing that we can take reciprocals of proportions and still get a true proportion. But they might give you that and tell you you're going to need this for this problem. So you might be able to see it written that way. Now, we can also do this. Have we talked about being able to exchange those two things? Can I flip the means? So we could have A over B equals sine of A over sine of B. And that's fine. Okay, that will still yield a result that is correct. Now, usually they don't do that because this proportion here, we're able to see A and A match up, right? B and B match up and inside that ratio. Here, the A and A are numerators and the B and B are denominators. This is just the general way that probably if we had 100 textbooks, 99 of them, we're going to write them this way. Okay? If not 100 of them. So, when we do this, we should cross multiply and get 15 sine of x equals 13 sine of 42, right? Okay? Sine of x. Do you know what x is? No. Okay? So right now, if I knew x was 30, that sine of 30 would be 0.5, right? If I knew x was 60, the sine of 60 would be like 0.866. If I knew what x was, I will know what that number that is hiding behind that symbol sine of x is, right? But I don't know x, so I don't know sine of x. Does that make sense? So sine of x, I'm going to call it my variable term or my variable phrase. Does that make sense? Okay? So that's my unknown. How do I get, so what 15 times an unknown is equal to 13 sine of 42. How do I get my 15 and my unknown separated?
The inverse.
Not yet. I need to divide by 15 first. Okay? I need to get these two things separated. Because that's a number. Sine of x is a number. I just don't know what it is. Okay? So it's like, maybe we can do this. Let's do it this way. And this will be a tool that we use in like college algebra quite a bit. Okay? You might even use it. Those of you that are in algebra 2 might use this. Let's say that let's write u to be sine of x. And now if I make the substitution, I get 15u is equal to 13 sine of 42. If I did that, solve for u now, what would you do? Divide by 15, right? So up here in the red, that's what I'm doing. I need to divide by 15 because the red and the blue now are the same thing.
I don't know, I like dividing by 15 sine 42 and then multiplying by 13 sine 42 and get it back on the other side.
All right, so we're going to have sine of x equals 13 sine of 42 over 15. Okay, so now we've got the variable term isolated, but it's still stuck inside the argument of the sine function. Okay, so I've got to do the sine inverse. So I'll sine inverse this left-hand side, and I will sine inverse the right-hand side. So the way that's going to be written then is x equals sine inverse, and then 13 sine of 42 over 15. Okay? Now, in my personal opinion, if you're going to use these red calculators, use the blue ones, use the TI-83s, 84s, have at it, but you can, at times, especially the more in-depth these types of questions get, and the more messy this thing looks, you can mess up parentheses pretty easily. So all I do, I'm going to grab Desmos. Why do I like Desmos? Because when I type it in as sine inverse of 13 sine of 42 divided by 15, it puts it in print that is exactly the same as what I wrote by hand. Now, why would I know, and I did this on purpose, when I get that negative, why do I know if that's wrong? What am I, because I'm looking for an angle measurement, right? And right now, we cannot have negative angle measurements. And I said right now. When we take trig, we'll talk about angle measurements being negative. Okay? So I need to know that I need to go to degrees. And when I go to degrees, did you guys get that number there?
Yeah.
Okay. So is that pretty close? Can we argue that 42 matches the 15, and because 13 is close to 15, that x should be close to 42, and 35.4 is pretty close to 42? That makes sense? Okay. Paris, you say you didn't get it? What calculator you got? The 31? Does anybody have a calculator that has one screen on it? Can I see? Lexi, yours? Are you getting these with that calculator? Okay. You gotta almost do everything backwards, right?
Yeah.
So these calculators, guys, you got one of these?
I got it.
You have to hit type in 42, and then hit the sign key, and then you might have to hit enter, and then times 13, hit enter, divide by 15, hit enter, and then second sign, and then hit enter, and it'll give you your number. Okay? And that's a pain in the butt, I think, but.
I did second sign, and then 13 times 32 sign, divide by 15, second sign. Yeah. I forgot the second sign.
Yeah, because you said you had 13 times. You didn't have this one in there?
Yeah, and then I divided it by 15, and then I forgot to do the opposite again.
What do you mean again?
Because I did that right before. Like, I hit my second sign, and I took 13 times 40.
With that one, you got to do it backwards. So hit. Actually, you.
I did that.
Okay. Okay.
Because I just do that before, and I do 13 times 2 sign before I divide by 15.
Okay. Can you remember all that?
I'm trying.
On test or quiz?
Yeah, I'm trying.
So this is just my suggestion. Like, there's a lot of places you can make a mistake there, right? And I think even the second sign, when you first type that in, that is maybe going to provide you an issue eventually, because that calculator is actually designed with its order of operations for you to work on these functions inside out. So you would actually do the sine inverse last.
Well, I still get it.
Yeah, right. But I don't know if I change the numbers that's going to happen. It might just be a coincidence. And some of the other algebra that we do this, like there's absolutely no question, and you really can't see there, can you?
I mean, I can.
If you want to move here, you can see. Rachel, can you see from sitting there?
Mm-hmm.
Okay. So if you type this in, I mean, there's actually no question on what the calculator is doing, right? It's just doing it what I wrote by hand. So I think that would be maybe just in regards to making sure that I'm safe and get my answers. That's what I would use. Yes.
All right. Mr. Free, you're a good teacher. What qualities do you think makes you a good teacher? But you, specifically you.
I don't know.
You have a good beard.
Yeah, good beard. You did. It's all right.
What's happening on There's red in there.
That was pizza. And that was like 2 weeks ago. So don't eat it.
I wasn't planning on it.
All right, so, yes. What?
I have to go like really bad.
Riley, that's a more local.
Yeah, hurry up.
Go in the trash can.
All right, so I got a question here. Draw this picture real quick. Draw this picture.
What the heck picture is that?
There's not every individual.
I don't know.
Toby said it, literally not.
I want to find the height of this building eventually.
I started off by finding a couple minutes up there.
I'm starting off going.
Really? I don't know. Wait, are we calling this together or out of that?
Either way.
Just draw it for now. Yes. If you put ham with it.
I'm saying,
If you put ham with it.
I agree.
and jalapeno. And it's sweet and the spice.
Okay, I can agree with that. Yeah.
Pineapple is
Pineapple.
Thank you.
Is that a right angle in the bottom right?
Yes.
Cool.
So one of your questions in your homework was like this, is I think it was talking about the height of a tree or something like that. And it asks you to essentially find, I think it staggers it, but find the height of this thing, you first need to find this distance right there. Okay? I think they call it A in your homework. Okay? So how can I go about finding X in this picture per the information they gave me? Okay, so why 148? Okay. So what is the supplement of 48? 132. Okay.
Now that one triangle has a distance and 2 angles.
Okay. Now, if I want to try to find this distance.
The other two, so you can get the angle up top.
Okay. So I need to use those two things together, correct? Because they're opposite. So I'm going to say sine of 35 over x. And the number one reason I know that I have to use the law of sines, or why I'm trying to use the law of sines, is I know that little sliver of a triangle there on the left is not a right triangle, correct? And if I need to find length, SOHCAHTOA is my thing to do, the thing to use. But if it's not a right triangle, then I have to amend SOHCAHTOA, and that's the law of sines that allows me to do that. So now the question is, that's kind of weird that took me straight to the law of sines in another course that I'm teaching that I haven't talked about in a couple months. We're not going to deal with that there, because so my second ratio cannot be the sine of 132. Why can it not be the sine of 132? Because I don't know that distance.
180 minus 133 minus 35.
Okay. So these green ones, if this was like y, and if I type in sine of 132 over y, what's the problem with that equation? Two variables. Okay. So you're telling me that I've got to take 35 plus 132. What's 35 plus 132?
Around 100.
167. So how big then is this angle right here? 13. Okay, so 13 degrees. So now can I say that 13 degrees and that 150 go together? So sine of 13 over 150. Now, this particular question is a little bit easier than the last one, because they're asking me to find a distance, right? So it's one less step. I don't have to use the inverse of the sine function. So I'm going to cross multiply again. I get x times sine of 13 equals 150 times sine of 35. Sine 13 is my coefficient over here for x, so divide by that. So you get 150 sine of 35 divided by sine of 13, right?
413.8.
Okay. So when we do this type of problem, we're going to have, so that's going to be a value that we have to round eventually, correct? Now, I do not want, because that's not my answer. My answer was find the height of the building, yes?
It was a two-part question. That's to find A, round the nearest tenth.
I'm not doing the homework question right now. So 150 sine of 35 over sine of 13. Okay? So I get 382.467. Is that okay with everybody? So that is the length of x. So now, and I'm going to write that. I'm just going to write this number down so I can remember it. So I'm going to go 382. Okay. Now, what do these little squiggly equal signs mean? Estimation, approximation. Okay. So, would you agree now that I've got a triangle here where this is approximately 382? This is a right triangle. You know this is 48, and that is h. What trig ratio will allow you to use with this 48, that segment there, and that segment there? Sine. That's opposite, and that's hypotenuse, right? So let's say the sine of 48 is equal to opposite over hypotenuse, correct? What do I multiply both sides by? 382. So 382 sine of 48 is going to be the height of my building, right? Okay. So let's talk about this. Let's do a little bit of analysis with our calculator here. Let's find the exact answer. Now, I know it says the nearest foot and all that kind of stuff, but let's find the exact answer without our calculator. Rounding. Okay? I could take that number right there, cut and paste it, or just retype it, and then type sine of 48, correct? That make sense? Okay? However, if I round it right there, then there's going to be rounding error in that height. Yes? Okay? Can I do this? Can I call this distance, I'm just going to call it h for hypotenuse. I call it h. Okay? Can I then say h times sine of 48 and do that? Because now the calculator is not using that number. It's using that number. Does that make sense? Okay. Here's my question. So that we know that's exact, at least to that 8, right? Let's just see how bad our answer would have been if we just used the 382.5. 382.5 times sine of 48. We get that number. So let me call this like W. Let me call this R. Oh, can't use R because it gives me polar coordinates. Let's call it P. So if I go W minus P, okay, divide that by W, okay, actually let's go P minus W. P minus W divided by P, okay, same thing, just the negative, yeah. So we get some error there, yes? Okay. So I want to make sure that we understand that if they're asking me to round to the nearest foot, in this case, even if I were to use 382, okay, if I were to use 382 as a rounded value to find the length of the building, I would have rounded this to 283, right? And or I said 284. And this one, using the exact value, I still rounded 284. Does that make sense? But if they ask me to round to the nearest tenth, that's the actual answer to the nearest tenth, right? If I would use 382, I would have rounded it to 283.9, obviously not the 284.2 that I'm looking for. Does that make sense, everybody? So when it's appropriate, you want to round as late as possible, okay? And we have technology at our disposal. It's free. It's very easy to use to keep our answers with very minimal rounding error. Okay, so I'm going to ask you to do those types of things on tests and quizzes here in the future as we move through. I'm going to ask you to leave them as exact answers, and then I'll ask you to leave it as the best rounded answer, and that best rounded answer is when we round as late as possible. Okay? Ambiguity. What's ambiguity mean? What's ambiguous mean?
I don't know what the word means.
What's vague mean?
Not clear.
Not clear. Okay? So ambiguity, kind of like a synonym. Okay? Ambiguity or ambiguous means left open to interpretation. So if I say I have a friend named Pat, do you know if Pat is a male or female?
Well, Pat's a male, I know.
Okay, so I asked this to Lucas Pritchard. Okay, his grandma's name is Patricia. His father's name is Patrick. Okay, they both go by Pat. Okay, so you don't know, right? If I just say Pat Pritchard, you don't know if I'm talking about our former girls basketball coach or if I'm talking about Mr. Pritchard down in the shop, right? Okay, so that's what we mean by ambiguous. It's left open to interpretation. We like in mathematics to eliminate all ambiguity. Okay, but there are times where it's impossible. Okay, when we talk about side-side angle, it is impossible to remove ambiguity. Okay, so if I were to give you a triangle like this, where I give you two sides and the angle or an angle that is outside those two sides, not between them. Okay, you have what we call the ambiguous case. I just want to demonstrate here what the ambiguous case is. Okay, and why we might have multiple results. So I'm going to control all this, copy, paste, get rid of the axes. All right, so 1, 2, 3, 1, 2, 3. Okay, so the way I set this up is that we have two figures here, two triangles that are exactly the same, correct? And I've zoomed in and out the same amount on both of them, so those are identical. If I was able to take the yellow one and lay on top of the white one, they are the same, okay? If I gave you, let's change this 45 to maybe 47. Let's take this 6.5, that first 6.5. Let's change that to that number. Okay. Now, here's the first part of the ambiguity situation. Let's say that I gave you this angle. Okay. So I gave you like a cardboard cutout of a 47-degree angle. Does that make sense? And then I gave you a segment that was 9 feet long, and then another segment that was 6.5 feet long, and I told you you had to connect these three things to make a triangle. Well, if you got your 47-degree angle, to make a triangle, doesn't the third side of your triangle have to follow this dotted line? That make sense? If it doesn't follow that dotted line, it's not 47 degrees. Well, then this segment here would have to touch that dotted line, right? Okay? And that point's really big, so let's make it a little bit more drastic here. Let's do that. Will this third segment touch that dotted line down there? So when I give you an angle side-side relationship, that information might actually lead me to no triangles at all. Does that make sense? Okay, you might not be able to create it. Okay, there might be a situation, and it's when this length here, the second length is 6.58, that we actually get one triangle. So let me see if I can view algebra, change this number to 6.58. Okay. Now, when I swing this around, okay, so it's not a complete triangle yet, right? So there'd be if we extend that segment or that ray, that's my third side, I need to find a point of intersection with that third side and the second side. And right there it would happen, right? Okay. There you have one triangle. So that would be a situation where we get one triangle with angle side-side. What kind of triangle do you think that is right now? It's a right triangle. So the only time that you get one triangle with angle side information is when you have a right triangle. Okay? Let's make this let's make the 6.58 number a little bit bigger. Let's go. That'll work. Okay? So right now, would you guys agree? So I put this one up to 9 as well. What was this, 47? And this was 7.7. Okay, so again, these two triangles are identical, correct? If I touch that one there, touch that one there, those are cut and paste on top. I think I might be a little zoomed in a little bit far on that one. But those are the same, yes? Huh? Oh, sorry. Thank you. Is that what you said, Cody?
Yeah.
I'm sorry.
Now it looks perfect.
So now they're perfect, right? Now they're identical. Okay? So if I gave every one of you a 47-degree angle, a 9-foot segment, and a 7.7-foot segment, and I said you have to put them together angle side side, some of you are going to create that yellow triangle, right? Some of you create the white triangle. And what you're going to find out? They're the same, right? Would that be a potential second triangle? Okay, so now I'd be looking, so just so everybody can see that potential triangle, it would be that one there. Still has a segment of 7.7, still has a segment of 9, still has my 47-degree angle right here. Those two triangles are not the same, right? The yellow one here and this red one are not the same triangle. Okay, so you see where it's left open to interpretation. The answer that I come up with is that the information for this one, because that angle right there and this angle up top are different than that angle there and that angle up top. This length here of this third side along the bottom is different than the length of this third side on the bottom, right? So you could have potentially two different triangles. Okay? Well, we want to be able to address. We know this should happen. The physics says this should happen, okay, or could happen. We want to see how would we address that. So this is how we address it. Okay? When it's like this, okay, we know if that's 47 degrees. Okay? I'm going to ask right now for GeoGebra to find me that angle. So 58.81. Now there's going to be a little bit of rounding error here because when I zoom in on this far enough, you see that the X really is on that dotted line, right? I'll try to zoom in as far as I can and make it as accurate as I can. So maybe something like that. That might still be a little bit off, okay? But, so if I do that, then this angle over here should be 58.74 as well, right? Okay? What would, just kind of help me out here, take 180 minus 58.74. And actually just go one decimal place. We'll change the rounding here to 121.3? Okay. Remember that number. Okay. So, when we have the ambiguous case, the result, what we'll do here, the only thing I come up with right here in this problem, the first thing that you're going to come up with to find anything is this angle here. Because you're going to take the sine of 47 and put it over that number, right? Then you're going to have this number, which you got to be a denominator, and it's got to go over the sine of that, right? So it's going to find you that angle, which was the 50, I forget what I said, 58.7. Okay? That'll give you 58.7 when we do that. You take sine, you work through it right now if you want to, it'll give you 58.7. Okay? The ambiguous case providing the second triangle, that angle is what compared to that 58.7? It's the supplement. Okay? And that is the check that we have to do to see if the ambiguous case actually produces two triangles. Okay? We have to see if I have 58.17 or 58.7, 47, you have enough angle measurement up here for a third angle, right? If I have 47, 121.3, you have enough left over for a third angle, correct? Okay? Let's say for some reason the first angle we found here was, let's say,
78. 3 degrees.
108.
Let's say this ends up being like 140. Okay? No, scratch that. Say this ends up being 40. Say this angle ends up being 40. Okay? If this angle was 40, what would this angle be? 140, right? If that's 140, what would this one have to be? It's 47, right? What's 40 plus 47 plus 140? 187, which is impossible for that. Okay? So then that would restrict me to only having one potential triangle. Does that make sense?
Yeah.
Okay? Right, so I'm just giving you like particular situations that could, when you go through the map, if that were to happen. Like I know it can't because of the size of these right now. So that's the ambiguous case. I'm not, like I said, I'm not going to spend a whole lot of time going through all these questions with you with the ambiguous case, just for the time's sake of where we're at, close to the end of the course exam. At the end of the year, when we have essentially May to cover things that are obviously post end of course exam, this might be something to come back to and spend a couple days on. Okay.
Have a good night.
Keep working on the assignment that I gave you yesterday.
Okay.
That's not due yet. That'll be due tomorrow. Tomorrow, law of cosines. Law of cosines, in my opinion, harder formula, much easier to use though.
Baby doesn't want to.
This is a boy or a girl? No, it's a it.
Man, we have great news for you. I don't want to know the gender. Well, it's
Those are my little brothers.
Why is it every time I try to guess the dog's gender?
Why do you have to guess a dog's gender?
Because, like, I would be at my friend's house, and I don't know
It's not like the dog's dressed.
I'll be like, how old is he? They're like, she? I'm like, oh. You know, like, I do that all the time.
Can't see if there's balls or not.
Do it.
There's a more appropriate way to say that.
How about you start it off with like, are they a boy or a girl?
Is it a boy or a girl?
I always say there. I never say he or she. I say what's their name. I always do.
What, I say what's it?
Just to say.
I say what's his name.
It's a dog. What's they all's name? What's they all's name?
If I want to be a boy, it will be a boy.
Is that what you're going to say when you have your first child? This is a girl. I don't care. I want it to be a boy.
The dog's going back in stuff right now.
Yeah, I know.
Huh? We're talking about like.
What exactly?
Dog's going back in stuff right
We go to science.
Yeah, no, you have to think about it. Like, okay, they are.
now. Yesterday.
We got in trouble. Still talking. I don't remember.
Have a good one.
Gremlin? Well, we're trying to get rid of
Market back up.
It was up 300 points earlier. So, like, net-wise, it's only...
Well, I'm just saying
it's up. I just can't... It won't tell me what the Dow is at, though.
Pardon the interruption. This is just an announcement regarding baseball practice. You are going to need to meet at the high school gym this evening, and practice will take place from 5:30 to 7:30. Again, that is high school baseball practice. Meet at the high school gym, and practice will take place from 5:30 to 7:30. Thank you.
Yeah. I can. Grab a seat in the hallway, Zeke, and I'll get you set up for it.
Pretty sure, because that I don't remember saying much about it.
It wasn't all day. Yeah, I know that was taking that long. Shut up. Yeah. He's gonna have to do this.
I don't know.
Never so like here. It was like, I just want things that one day coming. We're here. Thank you.
We're going to start by doing the last question on the homework. All right, so they give you that. Zeke, it should be open.